Okay. Okay. Just one more person. Okay. So welcome to the course. Let's say Hodge theory course. Okay. The data of the course I am collecting in my webpage. I think if you go to my webpage, and if you go to teaching and courses, and then the last item, Hodge theory, I am collecting all the information there. And as I said, usually I will not teach by iPad. I will teach in front of a webcam, but today, exceptionally, I can't do this one because I knew that there is no electricity in my apartment. Okay, so let's go to the course. Okay. So today is a kind of introduction to the course. So there might be some not rigorous statement. The idea is that from the next lecture, there will be more rigorous statements and theorems that we want to prove. But first, I wanted to make a kind of advertisement for Hodge theory, and not exactly the Hodge theory, but for the study of integrals. One of the origins of Hodge theory, and actually a lot of Breinstein mathematics has to do with the study of integrals 150 years ago. For example, I can say during the course, we will see that a lot of algebraic topology, a lot of algebraic geometry, complex geometry, differential equations comes from the study of integrals. So today I'm going to talk a little bit about starting from chapter 2 of my my book. If you have already looked the webpage of the course, you will see that there are 2 books of Claire Voisin, and I have put 1 book of mine, which will be published in soon, and the other one, which is still I am writing and with my former student Roberto Villaflor. Okay, so let's start. So the idea, as I said, a lot of good mathematics comes from the study of integrals. And okay, so maybe well, since I'm not used to write on the iPad, and from the next lecture I will start to write. So sorry that I am going to write in front of on top of my own book. Okay, anyway, as I said, this okay. Okay, so a class of integrals which appeared, let's say, before 90s are the so-called elliptic integrals. So which class of integral we are talking about? We will take a polynomial px. For the moment, just take degree 3. Degree of p equal to 3. And for simplicity, if you want, you assume that it is monic and it has a real root. So x minus t1, x minus t2, x minus t3. So ti's are real numbers. So and then you start making this, forming this dx over square root of px, and then you are integrating over consecutive root of p. So let's say, so if you take the x plane and the y-plane, and then you have this t1, t2, t3, and then you make this, you define the function y equal to square root of px. As you see, my iPad handwriting is not so good. That's why from the next talk it will be just usual writing on the paper. Okay, anyway. So if you make this the graph of this this function, it will be of course you can put in mathematics. Sorry, and you will see that there are curves like this, and at the end of the day we are. For example, if you take this A and B, T1 and T2, then we are computing in some sense this area. Anyway, I think the integrals are fundamental parts of our mathematics, and their study led to a lot of other different mathematics. And in particular, the people at the beginning, they wanted to compute integrals. Something that even before 19th century, it was became clear that you cannot compute these integrals. And anyway, this is not a rigorous statement, what means to compute. But in order to understand a little bit this concept of computing, that changed also by time. So I mean, something computing for a mathematician maybe 100 years ago was different from computing what we call now. Anyway, I think maybe one good exercise that you can do it. If px has repeated roots, this means that if one of these two ti's are equal, then if you put the integral in Mathematica, it will give you something in terms of some other well-known function. And in some sense, this means that let's say, one can compute. Another thing is that, I think in order to understand what means computing in this case, it is really to do this exercise. And actually, this exercise you can do with any software which computes integral. If px has repeated roots, then okay, we can compute it, and another thing. So let me write here. Okay, so computable 1 degree p is 3. P has repeated roots. Another one that which is also the exercise in my book, degree p equal to 1 and 2. And you might get bored saying that, okay, what's the matter to compute these integrals or not? But the idea, the basic idea that I'm going to talk about, that this has to do with some phenomenon in algebraic geometry, that the curve that you have at the end, I had this y equal to square root of px, and then I make to the 2 of both sides here, and then I will get this one. The idea of this computability in algebraic geometry leads to the fact that this is actually a rational curve. Actually, its topology is a sphere. And this one also, when it has repeated roots, after a kind of blow up that we are going to explain, it is still a sphere. So let's say a sphere. And the one that we were dealing with, and we say that it's this integral is not computable, it's some new integral, has to do that the topology of this y squared equal to px is an elliptic curve. So you see that try to understand the computability of integral leads to topology, because we have to understand the topology of algebraic varieties. We are leading to the classification of curves and algebraic geometry, rational curves, elliptic curves. And so even many people might have forgotten the algebraic topology or in algebraic geometry, these integrals, they have been very fundamental objects to produce more results in both areas. Okay, so let me, okay, maybe any question? Okay, let me go a little bit further. Okay, so suddenly I started to talk about spheres and torus, but let's explain a little bit more what is going on. First of all, I wrote my integral, maybe. Okay, just a moment. Okay. Okay, first I wrote my integral as in a usual calculus integral in the real domain. And one process that we have to do with this integral has to do with, we want to take it to complex domain. And so in this case, we will take P complex polynomial, degree 3 again. Then we will have these 3 roots, T1, T2, T3. And so in the complex domain, what we are doing, so the integration will be from one root to another root. Maybe one exercise also that in the book I have put that these integrals near to this T1, T3, they are converged, because it's not clear. You see that at A and B, this integrand is goes to infinity. So one has to prove that these integrals converge, and it is also it's not so difficult. And so first the process of these integrals is the complexification. So our integrals will be from one root to another root. And okay. And well, so one of the prerequisites of the course is the complex analysis. Something that in the complex analysis we learned that the integration doesn't depend on the path of integration. Maybe I still let me draw still the real picture. So now this is the x plane in complex. The previous one was x and y, but now this is the x complex plane. So there was T1 real, T2 real here, and we were integrating over this path. So in the complex analysis by Cauchy's theorem, one learns that this integration doesn't depend on the path of integration as far as you don't cross the other root. So this means that at the end you see that in T1, T2, T3, our square root is multi-valued. The square root, you can choose 2 values for it. And as far as, so this means that this path, the integration over this path is not allowed. So this, so the integration over this red path is not the same as the integration over this one. So let's So okay, so this we learn in complex analysis. Okay, another process during the complexification of these integrals is the introduction of this variable y. Okay, just so as I said, I put y equal to square root of px. I looked for its graph, and then okay, I said let's say just look at y equal y to p squared, and okay. So something that in the, maybe let's go to the other page. Maybe. So after the introduction of this variable y, and since we are in the complex domain, it is natural to introduce this this set. This is the set of x and y such that in C2, such that y squared equal to px. And the idea already around the 19th century and going to 20th century was that to integral our integrals to this new space. So maybe I draw again our path of integration. T1, T2, and then there was a path from T1 to T2. Let me just a moment. Just a moment, one moment. Okay, and some replacement again, which mainly done by Riemann, and so the idea was that this T1, T2 are a kind of poles or infinity points of our integrand. So let's just avoid this one and make some passes which turns around this T1, T2. And it doesn't hit this T1, T2 because in T1, T2, my integrand, dx over y, is goes to infinity. And you see that we have already replaced a square root of px by y. And the idea is that in the integrand part, in the domain of integration, we are going to do a little bit topology. And in the integrand part, there will be popping up concept of algebraic geometry like algebraic differential form and so on. Anyway, for the moment, y is the square root of px. So one next step in this process of understanding integral was that let's just try to integrate over this closed path, because remember that I complexified my x-plane, and now the passes have freedom to move. And if I put this one, let's call this one gamma, and the other one delta tilde. And this is also another very simple exercise that during the course, if you want, we can return back and do these exercises concretely. Our original integral was where dx over y over gamma. And it turns out that this integration over delta tilde, twice this one, is the integration over dx over y integrated over delta tilde. And the reason is very, 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 very simple. Why? So first of all, our paths are oriented. So this means that from T1 to T2. So let's say okay, this one. So why twice? This one is twice my original integral is integral of dxy over delta tilde. First of all, you remember, just imagine that this delta tilde is getting contracted to this path gamma. So when it so after contraction, we argue that at the end the integral doesn't change, and we already know that my integration converges on T1 and T2. So it's safe to say that well, let's imagine that delta T gets contract. But when it contracts, what it becomes? It becomes gamma. So that's me. So after contraction, let's say delta tilde becomes what? It is gamma plus minus gamma. Minus gamma means that the opposite direction. Okay, if you look at just this one, you will say, okay, then the integration over delta tilde is 0 because we are taking integration over gamma and then we are taking integration over minus gamma. And so they will cancel each other, but they will not cancel each other because remember that y is equal to square root of px. When we go with your gamma and then we return back with your gamma, the value of px changes because of this turning around T2 or turning around T1. This means that this minus will cancel with the minus coming from this square root of px, and at the end you will see that integration over delta, this is actually twice the original integration that you had. And anyway, in maybe if at the end of the lecture I will ask for questions if somebody wants to more detail. So we have already the next step of understanding our integral. We have replaced the domain of integration by some closed path, which has not to do with the which avoids the ramification points of my function square root of px. And this is good because I'm not supposed to take care about convergency of the integral and so on, because my function square root of px is well defined over this path delta tilde. Okay, so and now it comes another step of the process of our complexification. So the idea is that I want to think that I am integrating over this one. By the way, I think one of the main responsible for all this process must be considered Riemann, who is also responsible for the concept of Riemann surfaces and so on. But anyway, I think there are a lot of people around 19th century contributed to develop all these intuitions and so on. Okay, so the next idea is that I want to take the integration to this object, and actually the integration will be on a let's say something that during the course we will try to a little bit get familiar, the concept of the homology. But for the moment, just forget it. So let's say in this way, something that during the course that we will see, we will. One of let's say the first let's say 8 lectures during the course will be dedicated to understand the topology of algebraic varieties. This is one of the most simple algebraic varieties that we have. It's actually a curve, but in general we will try to understand the topology and what it means that to understand the topology in this simple example of elliptic curve, we will understand that what we will see that it is actually a torus. By the complex equation, it is not at all clear. So just remember that it is the equation is this one: x, y in C2 such that y squared is to px. And the point is that it is embedded in C2, but C2 is R4, because each coordinate has a real and imaginary part. And it's not at all clear what this object look like. And something that in during the course we will understand, it is actually a torus, and but one point removed, which it has to do with that our C2 is not compact. Usually in algebraic geometry, even topology, we would like to compactify the objects, and when we compactify, we will see that E is a torus minus 1 point. So this is a kind of let's say advertisement for, let's say, I think this comes 6 to 8 lectures of the course. We want to understand the topology of algebraic varieties. And remember that I was integrating over this X domain. And this X domain, so now this is the point. Now I am dealing with C2. So the pictures will not be rigorous. If I am in R2, I can put by software, I can write the graph of this guy. But in the complex domain, I will not use. We don't have precise pictures. And but remember that I was in the X plane. I had 3 roots: T1, T3, T2, and I was making passes around 2 roots, and then I was integrating over this. Well, I call this delta tilt. It now in the picture it is. I have put it gamma 1 and gamma 2, and as I said, we will actually prove that this E is a torus minus 1 point, and from this torus, we have projection to the X plane. X plane. So the next process in this study of integrals it becomes like this. That this path that you see actually, it comes from a closed path in this tori, and it is just the sake of notation that at the end my integrals became this one. So let's return back to. So at the end of the day. My integrals at the end they were reduced to something to this one. So let's say something that in the course. Well, I really don't want to assume that the people know all the machineries of algebraic topology. So the idea is that these passes will induce something in the homology, and there will be higher homologies and so on. And I will try to go slowly. And if somebody doesn't know the construction of homology and cohomologies, I will try to give few courses, few lectures to cover this part. But let me a little bit. Go in, since this is the introduction. So at the end of the day, during the course, what we will do, we will go to very broad context. So we will dealing with projectives, smooth projective varieties in some projective space. So this is smooth. And so so this has to do at the end that we have to compactify our elliptic curve. And something that we have to get familiar in during the courses, the our complex numbers, and at some point we will see that part of the theory can be done over arbitrary field. So something that we will slowly get familiar with is this homology that I said, n equal to 0, 1, 2, until 2n, where 2, let's say, let's call this m, this is m, 2n, oh sorry, this is n, and n is dimension, just a moment, okay, just where I was. Okay, and dimension of x. So this means that good part of the course we have to get to familiar higher order homologies and cohomologies, and actually at some point we will also develop the cohomologies. That at the end this index will appear on the top. So the integration, a lot of nice integration from calculus actually will be translated to this integration over delta. Let me say letter. Another part of the course, with few lectures we will invest on this one, is the integration. And actually for the integration we have to develop the concepts of algebraic de Rham cohomology. Algebraic de Rham cohomology. If you have done algebraic topology, you have already seen that usually one takes the de Rham cohomology using C-infinity forms, and it was a kind of observation by Atiyah-Hodge and by Grothendieck, that at the end of the day, these cohomologies of C-infinity cohomologies, you don't really need the category of all C-infinity function on X. You really need just the category of polynomial differential forms. And you already see that in our example, in example dx over y, we have not used any C-infinity form. And but the algebraic de Rham cohomology, and it's in particular its computational aspect, it's not so covered in the literature. If you go look at the Grothendieck's article, you will not see how to compute things with the data of hypercohomology, the de Rham cohomology that is written there. So one good few lectures also we will invest on developing this algebraic de Rham cohomology, and in order to have this and also to have these integrals. Okay, so maybe I took a few minutes. Well, I could name a different. Okay, I could use different name for this course, not Hodge theory, because at the end, what I'm saying that our main interest has to do with the integrals, their contribution, algebraic topology, algebraic geometry. But one of the main reasons that we are I called it Hodge theory, because we are interested also in the Hodge conjecture. And actually, the reason why we are interested in Hodge conjecture has to do with these integrals again. Maybe for this one, I write in my note. Okay. And maybe, I don't know if you know, the Hodge conjecture is one of the Millennium Prize problems. And I think, well, for me, the importance of the conjecture is not because it is worth 1 million. For me, the importance of this conjecture has to do that it is possible to think on this conjecture and produce a lot of good mathematics. I think the same philosophy with Fermat-Law's theorem. I mean, Fermat-Law's theorem, at the end of the day, the final solution, I think it's not really what is important, the mathematics that produced Fermat-Law's theorem before it was solved. And not the final solution is the most important piece of this kind of mathematics. For me, the same is true in the kind for the Hodge conjecture. And so during the course, what we will learn that how we can break this conjecture into pieces and what other problems it produces, what kind of contribution it makes in these small pieces they make in algebraic geometry, algebraic topology, and so on. So let me explain roughly the idea of Hodge conjecture. Well, first of all, this conjecture will be for, as I said, for projective varieties over complex numbers. And okay, something during the course I will a little bit explain that we need this guy, and this is a kind of we will see that it is a Z module. Let's say B plus some torsion, like Z, Zn, blah, 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 blah. For the moment, we will just forget the torsion part. At the end of the day, our homologies cohomologied with Z coefficients, which come from algebraic geometry, they will be Z modules. We will ignore the torsion part. They will be Z modules of finitely generated. They will be called, these will be Bethe numbers, so, and so on. Okay, so this is, and the most important thing is that this guy is, we will see that it is constructed using C infinity forms, C infinity functions. Remember that in the case of algebraic de Rham cohomology, I told you that in the next lecture, we will see that algebraic de Rham cohomology, we can construct it using polynomials. And it will make sense to talk about elements of algebraic de Rham cohomology over field. But this guy cannot be constructed in the framework algebraic geometry. Grothendieck and many other people tried to construct, but they landed on different cohomologies. For example, étale cohomology, crystalline cohomology, and a lot of different cohomology. But the point is that this, which we learned it is singular homology, it is purely topological objects, and it cannot be reproduced in the framework of algebraic geometry. Well, in any case, it's not again a rigorous statement. Okay, so, but the point is that, but the point is that we can produce elements of this guy, some elements of this guy by polynomials. How? If you take, we will try to do basics of algebraic geometry in this course. Okay, maybe for simplicity, let's call it, let's say, assume that if you want a dimension x equal to 2, so dimension, this is the complex dimension, so dimension real of x is, let's say it is 4. Okay, so, but the whole discussion is valid for any x, and actually the Hodge conjecture makes sense for any x. In this case that I am going to tell, it's already a theorem. Okay, anyway, we can consider sub-varieties. when I am saying sub-varieties, this is in the framework of, let's say, given, in the framework of algebraic geometry, this is given by zeros of polynomials. And in this case, for let's say let's say in the dimension 2 case, I can start talking about those which has dimension 1. So if don't be scared from these concepts of algebraic geometry that I am using, but the idea of the course is to try to get familiar with all these concepts during the course. And okay, so anyway, something that in the algebraic topology we'll learn, and during the course also we will a little bit invest on this part, that actually, so this is the complex dimension. So this is dimension y over real is 2. And again, something that we will see, that at the end of the day, y is, well, y can be singular. And these things also we will slowly we will take care. But at the end of the day, we will understand during the course that it's topology. After a kind of making it smooth, it's a kind of toroid with many handles, or with many holes. This is let's say a sphere with many holes. And so, and in particular, we will see that at the end, this guy y will induce element in H2XZ. And maybe so this is the what I am saying. Even so, that the whole H2XZ we cannot constructing in the framework of algebraic geometry, but there are elements that still we can construct by polynomials and so on. So in general, if dimension y is let's say n over 2, let's say n even, then let's say called m, then this y will be this y will be in Hm, because this is the complex, and the real dimension will be m. Okay, so maybe so. Okay, so let's try to finish. So let's go Hodge M XC, the Z module, the Z submodule of HNXZ generated by all these algebraic things. So, okay, if you look, make Google with the Hodge conjecture, you will land on Hodge decomposition, harmonic form, and so on. But the philosophy behind the Hodge conjecture, and actually, if you want, you can think and try to formulate it in a different way. The idea is that we want to understand this module, the submodule of the homology generated by let's say, let's call this algebraic cycles. So the basic idea of the Hodge conjecture that it gives. So let me. Okay, so let me. So let's write in this way. So the Hodge conjecture. Just a moment. I am making. Okay. Hodge conjecture. What it gives a criterion to it fixes a criterion to decide whether delta Hn xz is algebraic or not. What I mean with delta is algebraic or not is the same, what I told before. Whether it is a linear combination of cycles of this form. Anyway, the precise statement of the Hodge conjecture, we will learn it during the course, but the philosophy behind is this one. And maybe let me a little bit explain more about this. Just a moment. Okay. Okay, just a moment. Okay. Okay, let me write a little bit more. So, let me this. I told about that Hodge conjecture gives you a criterion. I can still a little bit talk about what is this criterion. So, I have this delta H on n xz. I want to decide whether it is supported in algebraic cycles in this the way that I explained you before. And so the Hodge conjecture say that if certain integral for certain omega h n the Rham x. As I said, well, this is one of the reasons why we will introduce this. We have to develop, first of all, this concept of algebraic de Rham cohomology. Let's okay. So the criterion, which is you will see during the course about the Hodge conjecture, is that certain integrals must be zero. By this one also we will recall, by de Rham theorem, if all the integrals are zero, then we will conclude that delta is torsion and basically zero. But if part of our integrals over delta is zero, delta is still might be a non-zero element. And we will see that during the course we will see what it means certain. This certain actually has to do with something called Hodge filtration. We will see that the Rham cohomology has a filtration which is called Hodge filtration, and using this Hodge filtration we can formulate Hodge conjecture precisely. So okay, so this is the let's say kind of introduction the course, and let me return back to the okay. So during the course just a moment, presenting, not to present. Okay. 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 So during the course, we want to really see all the details that today I was talking about. So one thing is cohomology theories. Actually, I decided next lecture I will start with the check cohomology. And then I will try to recover check singular homology from check cohomology. This will be mainly for the domain of integration, and then we will start doing the topology of algebraic varieties. So let me say maybe I will tell just here. So if you look at my book, chapter 5, we will start learning Lefschetz theorem, which are theorems about the topology of smooth projective varieties. And after this one, we will invest on this algebraic de Rham cohomology. If you have not seen finity de Rham cohomology, that's okay. Then I will repeat also the basics of the classical de Rham cohomology. And then once this is done, and once we define algebraic de Rham cohomology, we will define the Hodge filtration, and then we will have the integrations. We can introduce immediately the concept, the Hodge conjecture. Then we will go to Hodge conjecture in dimension 2, which is called Lefschetz 1-1 theorem. We will try to understand and prove Lefschetz 1-1 theorem. Okay, for now, this is the course. Just a moment. Felipe?
Oi.
Pode parar a gravação?